So this is our third set of slides within this module 4, and these three really are just recapping everything that I've said before. In fact, the whole unit, you're going to find redundancy in what I'm saying. And part of that redundancy is purposely built in because some of these concepts can get a little sticky for some students, and some of what I'm going to offer at the near the middle and the end of this unit is some of the trickiest parts of the semester when we talk about atmospheric circulation. So definitely, return to these smaller little slide sets as you need to. So what we were saying is that wind wants to move across perpendicular to these isolines, and these isolines are measuring barometric pressure. And in this case, the barometric pressure interval is changing by 4 units. So we've got 1028 as a barometric pressure here at the high pressure central. We reduce that barometric pressure by 4, so we're at 1024, another 4, 1020, 1016, and so on. So we know that as we're moving across here, I have to travel a lot of space before I lose 4 units of pressure. So this wind's not going to move very fast. As the rate of change increases as we're traveling across space, so we're introducing this geography, we're changing locations from one location to another, the pressure starts to diminish more and more quickly, which means the pressure gradient is increased, which means my wind velocity is going to increase. If we sort of imagine this in terms of density of the atmosphere, here we've got a lot of air pressure that's falling here. We've got a lot of dense, fast-moving particles here that just want to get out of here, and they're going to move across to this low pressure location here, and then they're going to lift again. All right, so this is our general scenario. Now, we had mentioned in the last little slide set that we get some rotation out of this because of the Coriolis force, and so these high and low pressure cells are going to spin. So in the northern hemisphere, we said that the spin out of high pressure cells is clockwise, and the low pressure cell in the northern hemisphere is counterclockwise. The opposite is true for the southern hemisphere. So the southern hemisphere, we said, is got a counterclockwise spin, and that occurs around high pressure cells, and that means that the low pressure cells in the southern hemisphere are clockwise. So what we have drawn here is a North American scenario. So if you find my cursor, the air is falling here. It hits the surface of the earth here. So this is where my pressure is going to be the greatest. All those marbles, all that air is going to want to find its way across to this low pressure cell. If there's a low pressure cell over here and one over here, all this air is going to rotate through there. But because this high is spinning clockwise, that air is going to spin, and it's going to spin out of the high, find its way over to the low, and then rotate counterclockwise into the low, and then that air is going to be lifted up through, and then you can see we're generating a cloud mass out of that low. So my low here is going to maybe produce a small localized cloud. If I get enough clouds, I remember I'm moving latent heat. So the more cloud mass I produce, the more energy I'm going to be storing up here. The bigger the storage of energy I have here, the bigger the potential for a larger storm. So these low pressure cells are generally unstable because we're moving air up, and we're going to generate a storage and then a later emission or rain or snow, if you will, of that energy in its physical form. And then we're going to come around, and what energy is left is going to find its way back to a high, or where a high is dropping, and then we're going to drop that energy again. So we've got this rotational effect here, and I hope that you like this diagram. For me, it does a really good job of showing how those spins work a little bit better three-dimensionally. The other one on the other slide was really just two-dimensional. It was just showing from overhead. What also needs to be recognized is that this low, all lows, are called cyclones. So think of, an alternate name to a cyclone. You might think tornado, right? So a tornado is a low pressure phenomena. In Australia, cyclones are called willy willies. They're like a little tornadic event. We can consider dust devils as cyclones or water spouts as cyclones, right? Our big winter storms, we often don't think about them as cyclones, but they're rotating counterclockwise as well, and they're lifting, and they have clouds, right? And we know they have clouds because they're shedding snow on us. So those are cyclones as well. When all of that water is shed, and it's shed as it's moving across to the high, we're dropping that energy, and it's the opposite of a cyclone, so it's an anti. So we've got an anticyclone is an alternate name for the high pressure cell. So a couple more diagrams. These are from your textbook. And so what we've got, just to combine this with adiabatic lifting and falling, is we've got a low pressure cell that's highly energized, and we're going to lift, 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 lift. As we're lifting, we're cooling. But the air parcel is expanding, and we expand that. Remember that at a point when we've got equilibrium, there's no more movement up. The air pressure here in what was an expanding air mass is the same as the surrounding air mass. So at the point where the air that was lifting becomes more dense than the surrounding air, then it starts to fall. As it falls, it starts to compress. And as it's compressing and it's coming down, 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 it's cooler air, but it's starting to compress and become warm. All right. So I've got this nice warm air mass now that is generated because of compression upon falling to the surface of the earth where we've got a high pressure zone. Generally, this low pressure zone here is the result of superficial heating. So sunlight's coming in, it's warming the surface of the earth. That surface of the earth is going to radiate heat and excite the molecules at the lower level of the atmosphere, cause them to move rapidly. If they've got room, they're going to expand, and as they expand, they're going to lift. All right, so here is this rotation that we just gave you in the previous slide over the surface of the earth here. This diagram pairs nicely with the three-dimensional diagram that I gave you before. So if the rotation in that diagram is a little bit hard to follow, here's our anticyclone, no clouds. All the clouds that were in the atmosphere were shed out. So we've got nice sunny skies. That's important. We'll talk about that in a few minutes. We're descending that air. We're driving it across. Now I've got a warm environment here where I'm going to have convergence. So that means that the air is coming in from a number of different places. It's converging on a location. And then we're going to have lifting. So I better make sure that I tell you, if this is convergence, this is diverging. So diverging is to split. So we're splitting the air mass that's falling here. Think of all those marbles falling. Now the marbles are coming together and they're lifting. We're going to take the water, which is in vapor form, that's lifted along with the air mass, up at the level where condensation takes place. We're going to generate a cloud. All right. Fantastic.